recording, and then also I start sharing. Do you see this shared screen?
Yes, sir.
Okay. So we'll straight away go to the subject, and our discussion for today is pericyclic reactions. I expected that more participants will be there. I don't know the reason why today is only 20, 22, 23 people are present. If it is for Lakshmi Puja, I don't know whether it is, there was no vacation, I mean, there is no holiday from USTM side. So we have to take class. Anyway, pericyclic reactions. Some of you just give 1 or 2 points about pericyclic reaction. Who is there? Let me see. Say Daisy is there. Can come on, Daisy. You tell something about pericyclic reaction.
So in pericyclic,
Yes, tell something about pericyclic reactions.
here reaction goes through concerted mechanism. The cyclic
Concerted
product is
mechanism.
formed.
Yes.
Yes. Cyclic product is formed.
Cyclic product, but always okay, cyclic product, but not always cyclic product is going to be formed. Anything 1 or 2 point more? All right, so let us start. Pericyclic reactions is a completely different type of photochemistry. Photochemistry will be handled by Gaji sir. He'll be taking, I think Gaji sir, what he's taking now at present, what is he is doing?
So mass spectroscopy.
No, that is the from spectroscopy paper. From organic chemistry, what is that? What he is doing?
Heterocyclics.
Recyclics, no? Okay. So after that, he will take up this photochemistry. The photochemistry and pericyclic reaction, they go together. You have to have some idea about photochemistry also when we study pericyclic reactions. But pericyclic reaction also take place in presence of heat. But it is unusual, not a normal type of reactions that you have come across. It involves some of the a transition state which passes through some cyclic transition state. The transition state is cyclic, involving some pi electrons and also in some cases sigma bonds as well. So let us go to the definition. There is a concerted bond reorganization, and essential bonding changes occur with a cyclic array of participating atomic center. Okay, that means it is passing through a cyclic transition state. The reaction do not involve any intermediate formation. So this is another important point. Is a concerted mechanism, that means simultaneously bond breaking, bond formation take place, and does not have any any intermediate. There is a transition state, which is a cyclic transition state, involve a cyclic transition state, and there is no intermediate formation, either radical or ion. So this is an important point about this pericyclic reactions. Then also these are, once it is not having any intermediate, it's not affected by polar reagent. Even solvent changes, the polar solvent, non-polar solvent does not have any effect on the rate of this reaction. Radical initiators also, because there is nothing like that. These are however influenced, this is an important point, these are however influenced only thermally or photochemically. thermal state, reactants in ground state of electronic ground state. And when we talk of excited state, this is electronic excited state. So the reaction will take place either thermally or photochemical. When it is photochemical, it is the electronic excitation state where the absorption of energy will take place and the electrons are converted to the higher energy level. So this is what is the definition. Okay, let us come to something more. Classification. Uh, any idea about the classification of these reactions? Somebody name one or two type of pericyclic reaction. Come on.
So electrocyclization,
The
cycloaddition,
electrocyclization, that is called electrocyclic reaction. Yes. Cycloaddition. Then any other?
sigmatropic reaction,
Sigmatropic reaction. Yes.
then group transfer reactions,
Yeah, this is, yes, you see here. Electrocyclic reaction, cycloaddition reaction, sigmatropic reaction, caliotropic reactions. This caliotropic, okay, is a term we'll be explaining it, and group transfer reactions. So these are different classes of this type of reaction, that is pericyclic reactions. All right. So let us quickly come one by one. First of all, we'll explain one by one all these type of reactions. First is electrocyclic reaction. What is that electrocyclic reaction? An intramolecular, if we just see here, this is an intramolecular. Let me take this pen and use a new one here. Suppose this one. Yes. Intramolecular reactions which involve sigma bond is formed between end of the conjugated pi system. So that means it will involve a conjugated pi system. This conjugated pi system, the product will have one less number of pi bond than the reactant. So what it will involve? It will involve a conjugated pi system. So at least minimum we should have a two conjugated pi bond. It may be having 3, it may be 4, it may be 5, it may be 6. So that number of conjugated pi electron system, and when it is reacted either thermally or photochemically, and we get a cyclic product. That is your electrocyclic reactions. If we see here, these are the different examples that we find here. We have here, say, this is a cyclotrine, conjugated cyclotrine, single bond. So what happens here? The intermolecular sigma bond is in which a sigma bond is formed between the end of the conjugated pi system. This end of the pi system. The end of the pi system is here. You see here, this is end of the pi system here. This is the end of the pi system here. So it starts this way. So we have a new sigma bond formed here. This is the new sigma bond that has formed. And so here I did not give this arrow. It can be shown like this one. This arrow is going here, and this is forming this pi bond. Pi bond is coming there. But you see, is writing this type of arrow shifting is not a very correct way of it. It is forming that transition state through which it is. And the condition of the reaction, it may have thermal, it may take under thermal condition, or it may take under photochemical condition. But we'll have a new sigma bond form, which will be in the end of this, and the resultant product will have one pi bond less than the parent bond. So parent reactant had 3 pi bond. Now we will be having 2 pi bond. So one less. The product has one less number of pi bond than the reactant. So these are the things that we get in your electrocyclic reactions. So if I have this one, suppose diene system. So we get a cyclobutene reaction. If we have a tetraene, so there are 4 pi bond. In the reactant, we have got 3, and the new sigma bond is formed here. This is the new sigma bond, and the reaction takes place in either thermally or photochemically. We can show it this reaction like this one. Oh, this is too sensitive. Okay, I come here, then this electron moves here. Oh, goodness. Okay, so and this is here, and this is here. So what we have in the product, we find there is a new sigma bond formed, but this red line is there, and then the resultant product will have 1 pi bond less. Okay, this is simple definition. Coming to the next category, that is cycloaddition reaction. In cycloaddition reaction, what 2 different pi bond containing molecules add together to form a cyclic compound. Pi bonded system will add together to form a cyclic. Each of the reactant lose 1 pi bond, and the and the resulting new. Sorry, this is I think this was not noticed properly. This is okay. The resultant new cyclic product has 2 new sigma bond. If we take example, it will be clear here. Cycloaddition reaction, this is 4 pi system and this is 2 pi system, and here the reaction takes place thermally. The 2 of them add together. You can show it this way also. And each of these reactions, so this is 4 pi and 2 pi, addition of 4 pi 2 pi system, giving a cyclohexene. This will lose 1 pi electron. This has 2 pi electron. In the product, we'll have 1 of them. This had 1 pi electron. This had 1 pi electron. This is going to have no pi electron at all. And we'll have these 2 new sigma bonds. So these are the features of the cycloaddition reactions. And here you find 2 pi and 2 pi. 2 pi and 2 pi cycloaddition. But here, what we'll find that this does not take place under thermal condition, it takes place under photochemical condition. Here also we find that 2 new sigma bond is formed, and each one will lose 1 pi electron. That means it had 1, so it will become 0 pi. Here it has also 1, so this also will losing 1. So we get this. Ultimately, the system will have this cyclobutane. So that is cycloaddition reaction. This is simple definition. But this 4 pi 2 pi system was a known reaction earlier carried out earlier than when the systematic study was started. Who started this? Who is the father of this pericyclic reaction?
Sir, this is Diels-Alder reaction.
This is Diels-Alder. That is what I'm telling. This is Diels-Alder reaction. So it is done much earlier than the actually pericyclic reaction systematic study was done. Who is the father of pericyclic reaction?
Sir, Hoffman and Woodward.
Woodward and Hoffman. Yes. Woodward as an old, mature organic chemist, and Hoffman was a young scientist at that time. So they are the one. After that, then also a Japanese group is there, Fukui is there, and some other. So Fukui and co-workers. So they are the one. They got Nobel Prize for this reactions, and they have given all the theory about that. Why this reaction? How this reaction take place, and all these things. So it appears to be very simple reactions, but its stereochemistry is quite interesting. That is what we are going to study. Next, we find Sigmatropic rearrangement. So this is an interesting case that we see here. Sigmatropic rearrangement. Sigmatropic rearrangement. In this case, what happens? In sigmatropic rearrangement, a sigma bond is broken in a reactant, a new sigma bond is formed in the product, and the pi bonds rearranged. That means the number of pi bonds remains same. The number of pi bond remains same. So this is also a conjugated pi electron system where a sigma bond is broken, a new sigma bond is formed, and the number of the pi electron rearrange themselves, but the pi electron total number remains same. Again, when the sigma bond breaking is concerned, the sigma bond that breaks, it may be in the middle of the molecule, or it may be at the end of the molecule, and accordingly they are named also. So that is a sigmatropic rearrangement. We have to see actual reaction reason for this. So if I see this particular product, so this is what 1, 2, 3, 4, 5, 1, 5 diene, and we have given here one methyl group as a substituent, so as to see whether we are getting. If we don't give the methyl group, we don't understand that whether the reaction has actually taken place or not taken place. But once we give this one, our product has got a different. The product is going to tell that there is some rearrangement happening. Now, this is called 3,3 sigmatropic shift. Where what happens, this sigma bond is broken and this new sigma bond is formed. Now, why this is called 3,3 sigmatropic shift, that also we have to understand when we take up the details of this one. And this is, and so it had, the reactant had 2 pi bond, the product is also having 2 pi bond. One sigma bond is broken here, and this is in the middle of the molecule, and the one new sigma bond is formed here. In the middle one, what we find here, this is going to be 1,5 sigmatropic shift. Why it is 1,5 sigmatropic shift? We'll take up that one when we go for the details of these reactions. Now here I have given, this is actually, if we can take it also as H, but we have given here D just to show that it is this particular. So this is here, this sigma bond is broken, this sigma bond is formed. This new sigma bond is formed here. And the number of the pi bond which was there, also got rearranged. How it happens? This is what we are going to study. All right. So this is just the definition we have taken now. Another type is group transfer reactions. Now, when we talk of group transfer reaction, the fourth type, that is group transfer reaction, the type of reaction, the group transfer reaction, in which one or more group of atoms transfer from one molecule to the other molecule, to another molecule. In this reaction, both molecules are joined together by a sigma bond. So this is what is a group transfer reaction. One type of group transfer reaction, this is called in reaction. Again, this takes place here thermally, under thermal condition. Photochemical, we have, no, this will take under thermal condition. And we have got an allylic system here. This is not a conjugated diene here, but this sigma bond is broken here. You see here, this is sigma bond is breaking down, and this new sigma bond is formed here. So this is what is going to be, this sigma bond is getting formed here. So why this is, how this is happening, what is the theory of this? This is what we are doing. The other one is Stereotropic reaction. That Stereotropic reaction I have not given here. Once we take this reactions, that type, we'll be taking that one in details. All right, so if I just go back, we see here this. Actually, if I see here electrocyclic reaction, this electrocyclic reaction, there is a cyclic transition state happening here, and this is the cyclic transition state that is going to happen. And if I come to cycloaddition reaction, here when the reaction take place, again the cyclic transition state will involve something like this. This is the cyclic transition state. And when we come to what is called this your sigmatropic rearrangement, you find here this new bond is formed here and this bond is broken. So the cyclic transition state involved will be something like this. This is the so everywhere there is a cyclic transition state that is going to happen. And in reaction also we have got this cyclic transition state will be involving this atoms and groups. All right. So this is about your simple definition about all these different classes of pericyclic reactions. Pericyclic reactions. Now let us take one by one. First one is electrocyclic reaction. Already we have taken what is an electrocyclic reaction. An intramolecular reaction in which a sigma bond is formed between end of a conjugated pi system. The product has one less number of pi bond than the reactant. And this going to the same example I am giving here again. So this is a triene system. It has 3 double bond. The product will have 2 double bond and the new sigma bond is formed here. This has got 2 double bond conjugated. The double bond has to be in conjugated system. And we have got here one double bond will reduce, pi bond will reduce by 1 and the new sigma bond will be formed. Here it is a tetraene system, and we have got in the product we'll have a triene. Actually it is octatriene, 1, 3, 5 octatriene, and this new sigma bond is formed here. And here what you see here, the reaction will take place. The reaction will take place thermally or photochemically in all of them. But when we have seen example of cycloaddition, when we have taken what was there, 4 plus 2 cycloaddition take place under thermal condition, and 2 plus 2 cycloaddition take place under photochemical condition. Why that happens here and why it is like this one, this is what once we have to, so our theory becomes more important than the reaction itself. And once we understand the theory, now when we are taking example of this type of simple one, there is nothing, it is very simple, it appears to be very simple. So let us take, if we, now when we have taken the example of that nature that that we have shown in the last, in our, what is called, in our last slide, what we have seen that substituted, simple polyene when we have taken, the reaction is appears to be very simple. But when we take substituted reaction, give interesting results. That is what. So and now you have to be very careful. We take examples first. Let us take here. Now this is a triene system. Okay, this pointer is very, we have to locate it. It is so small, not visible. So this is a triene, but we have got 2 methyl group in this position, and this name you see, trans, cis, trans, 2, 4, 6 octatriene. This is 8. 1, 2, 3, 4, 5, 6, 7, 8. Why it is trans, cis, trans? These two, this methyl group and this group is trans. This double bond is trans in the trans configuration. This one in the cis configuration. This one is again in the trans configuration. So the name is trans, cis, trans. 2, 4, 6. This is 2. This is 4. This is 6. 2, 4, 6. Octatriene, right? Now, when this is heated, means thermal condition, we get this product. So what will be the product? The product will be, you can simply write down by doing this cyclic transition state and write down this. So this is the new sigma bond that is formed and the pi bond will shift their position. I think you got the point. But the methyl group that will be coming here in these two positions are found to be Cs. Just see, this is Cs. And if we take this one, where this is, you see, now this is Cs. This double bond is in the Cs configuration. This double bond is also in the Cs configuration, the two groups which are there. Are you getting my point? Hello? Yes or no?
Yes, sir.
Yes.
Okay.
Sir.
Okay, these are in the Cs configuration. Again, this one is in the trans. So it is Cs trans 2, 4, 6 octatrine. And here, when we do this thermal reaction, thermal heat it, just heat it, we get this two methyl group that comes in position, these two positions. Your name has to, double bond has to start from here. 1, 2, 3, 4, 5. This methyl group becomes 5 and 6. Not methyl group should not be as 1. I think you know that one. That nomenclature you have to be careful. So it is trans. The methyl group appears to be trans dimethyl. And here what we get, when the configuration was here of this night, it is Cs. Let me rub this one, otherwise it has become too much of when I rub it. Okay, now it is clear. So this is what we see. This is, we get here in this case, this is your Cs product, and here we get trans when our configuration of this triene is of this nature. But if we do it photochemically, when we do photochemical reaction of the same one, this one gives you this Cs product, and this one gives you trans. So, can you tell me why it is like this? So that becomes quite, now the confusion starts. The confusion starts means what? When we are going to Cs, get Cs, and when, under what condition we are going to get trans. Now, see next one. This is trans, you see here. This is your, oh my goodness, my pointer is here. This is, now this is trans, and here we will be getting a butene. But here the product, the methyl group that we find are in the trans configuration. This is in the trans configuration. But in this case, the first case when it was there, this is also trans, but here we got Cs configuration. I think he's giving me warning, so I have to finish it by 10 minutes more. We have got 10 minutes more. Okay. And here when we take this Cs and trans configuration 2,4-hexatrine and heat it thermally, we get this one and this one. That means that is the Cs product we get. But the same thing when we do it for photochemically, we get just the opposite product. Photochemically, when we carry out, we get this. This was the trans product from this and Cis product from this. Now, is it not confusing? Or you are okay with this? Give me the reply, because we are left with just 8-9 minutes. Come on. Huh? Now the confusion starts. Now the confusion starts. Now we have to see that we get rid of our confusion. This is what is our challenge. So suppose something you are given this type of a reactant. Now it is very difficult to remember that this is no, you cannot memorize that. No, I'll be getting here C's. But I can change this one in any way I like, because this configuration I can change it. I can write this one, this side, this one, this side, and so many things we can do with the reactor. Now that the product that you are going to get, what it is, whether we are getting the cis product or trans product, you don't know. That means you will be quite confusing. And also here you find in the thermal condition you get this product. Under photochemical condition from this one again you get this product. Again, when you have this type of double bond, what we get? You get thermally you get the trans product, photochemically you get the cis product. So it's quite confusing. I also will have confusion if I don't know exactly how it has happened. I will have confusion. But one thing you should take out from here. Now here, this is very much stereochemistry is almost like a certain what it is. We take this one, we get this. We get this, take this one, photochemically, we get this. What do you say? What type of reactions they are? Now, and they are reversible. Now we can have ring opening also. When we ring open this one, we get this. The reverse is also true. If we start with this one, you see, this is reversible. You start with this one, we should get this one. We start with this one under photochemical condition, we get this under thermal condition. So it is very, very confusing. But one thing is sure that what it is, these reactions are they not very much stereoselective and also stereospecific? Yes or no?
Yes, sir. Yes, sir.
They are very much stereoselective as well as stereospecific. So it exactly fits into this definition of stereoselectivity and stereospecificity. But now you get here cis product with thermal condition, but with photochemical condition you get here trans. Again, from this one, when it is diene, you get thermal condition, you get trans, photochemical condition, you get cis. That means there is some relationship of getting which stereochemical product or which stereoisomer will be getting, or from which stereoisomer will get what type of configuration of the reactant when the ring opening takes place will depend on what? What is that means reaction, this stereospecificity and this stereoselectivity is very much dependent on what? Tell me. Is dependent on what? It is dependent on something. This
Heat and light. Sir, depended on heat or light.
Only heat and light? No.
Substrate also, sir.
But substrate, what is the what aspect of the substrate? You see, it depends on what? You see, it depends on the stereospecificity depends on number of pi bonds. Here the number of pi bond is what? 3. Number of pi bond is 3. Here number of pi bond is how many? In this case, lower case, number of pi bond is 2. If we generalize it, this is odd number. This is odd number, and this one is even number.
Even number.
So when we take even number, we get one type of product. Even. So it is dependent on the yeah, number of the pi bond, and also it is dependent on whether we take the reaction under thermal condition or photochemical condition. So this is what is here. So we are, but still we are not sure which one. I mean, we are really under a lot of confusion which one will get back. But one thing is sure that this stereospecificity and stereoselectivity is dependent on number of pi bond and as well as number of pi bonds. But number of pi bonds, two things. One is odd number and other is even number. Under what number, odd number of pi bond, we get one type of product, and with even number of pi bond, we get another type of product. And also whether the reaction is thermal or photochemical. So I think we have to stop here because we'll be having very less time. Less time means it is 2 minutes left, and also we'll be having this. So I go back. I think anything you want to ask. Come on, we are still having 2 minutes, more than 2 minutes time to stop here, and then again we have to stop. So I think if we have to do recording, we have to do recording in one go. Come on, do you have anything to ask? Huh? Hello, come on. I find here 24 people have joined only, but all numbers are not there with me. Are you in a position to take all the numbers? Somebody today, Kannaki is not there, no? Is she there, Kannaki? I stop share. I sharing and then I go here. Tell me. Hello, Daisy. Oh, Kannaki is there. I find she is there. Hello, Kannaki.
Yes,
Kannaki, listen. I am left with only 1.5 minutes. Come on. Can you give me the attendance sheet? Pass on the attendance sheet to me. Acha. And Daisy, anything you have to ask about this? Huh?
So how the reaction takes place?
How the
Or
reaction take place?
there is
Yes. So next day when we
the
come,
mysterious events.
yeah, next day when we come, we have to talk about the theory of this. So just getting few seconds left. I think I end it here, and then again you let us rejoin. I end the reaction here. I mean this sharing here today, and you just join